So our next talk that's coming up here will be by Thomas Graf, who's been helping us with the setup for the conference. Thank you, Thomas, for that. And the title of the talk is on the slide there. So take it away.
Thanks a lot, Ben. Actually, before I start, I would like to take a moment to thank Ben and Justin for organizing this conference. I think this is absolutely amazing. Thank you very much, guys. This is awesome. All right, what I want to talk about is intent-based networking with an option to offload to hardware. I want to achieve that in a vendor-neutral way to allow vendors to compete against each other and do innovation while preserving standards, open standards, and have a fully open source solution. Before I dig into the hardware details, I would like to provide you with some context because we have a higher level vision which evolves around user intent. And I would like you to show the path from user intent all the way down, how that maps into an SR-IOV use case where we can accelerate our intent-driven use cases with hardware support. Once I've established that model, I will propose a model that we're working on in the open source community, and I will give a status update on where we stand. And John Fassman, who is going after me, will dig into some more of the technical details and will present and demo code that already exists that will allow OVS to get to the next level of performance. So typically, managing legacy forwarding devices has been opening up service tickets and network operations would resolve the service ticket and I would get back to you. Might have taken a while. We resolved that with SDN, right? Everybody's aware of that. So we now have network APIs, but as an application developer, do we really care about network-specific details? Do we really care about VXLAN, VLAN, virtual networks? We don't. An application developer or somebody deploying an application does not want to care about whether it's a VXLAN overlay, whether it's a VLAN-based network segmentation, or how many hops are there between my application A and my application B. For that specific reason, we're proposing a concept called Groupees Policy, which evolves around user intent. The vision is, instead of allowing to define how to do it, how to implement a specific policy, we require the user to specify what he wants to achieve. So instead of providing an API which says, spawn this VM and attach it to VLAN number 10, because I know that my other applications are in the same VLAN, so they can talk to each other, we're proposing to allow the user to define so-called endpoint groups, where you can define constraints between those endpoint groups. And a VM or some form of container or even a bare metal process would be a member of that group. I have an example here on the slide. So on the right side, we will have a group called application, which might contain a number of VMs or containers. And on the left side, we have a group called WAN, which would represent the internet or my users. And then I create a so-called contract, which defines the relationship between these groups. What I want to achieve in this specific case is that I want all my users connecting to the application to be only be able to do so when they connect through port 8080. And I want all connections between going to the application to be local balanced. So I create a service chain which directs all traffic through a load balancer. On the reverse side, on the packets that go from the application back to the internet, I would like to automatically allow all related packets, meaning that if it's known to the connection tracker, it should let it through. If it's an ICMP packet that is related to the initial request, it should go through. That's all I need to specify. There's no reason I need to specify anything further for a simple use case like that. But the fact is, if you're utilizing existing network APIs, you would need to create VLANs, you would need to create some form of overlay, you would need to create awareness on which specific IP addresses these applications are running on. You would need to ensure that you have either L2 or L3 connectivity inside your data center, and you need to make sure that you have a routing entry on your edge, make sure that you can reach your actual application. Groupees policy allows you to specify the contract in a way that makes it possible to reuse and consume a contract multiple times. So in this specific example, having an application group, that specific contract could be consumed from multiple consumer groups. So you could have two specific classes of clients, and you could have a client group A which consumes a basic contract, and you could have another consumer group which might have paid for a premium service and which is consuming a contract with additional constraints in terms of it might get you better QoS settings throughout your network. Policy or intent is not defined by a single instance, right? There's not one person writing the policy. You have to take into account all the sources which define the policy that you have to deploy in your data center. The example that I just showed would be the intent on top, which specifies which applications can talk to each other. On the same time, you'll have operational constraints, which would be how you want to run your data center. That might be, if you're doing encryption, that might be how you want to do that encryption, when you need to do encryption, where you want to deploy specific VMs. You have governance aspects, and you have capabilities and state. We'll get to the capabilities. In particular, John will talk about that on a hardware-specific front. And you also have state that is given back to you, and you would take that into account, and you continuously merge all these policy sources and build a model of intent that you can use. All of this leads to what I personally call intent-driven networking, which means if you have this policy model and you know which applications are supposed to talk to each other, you can use that context, that information to do network switching or network routing automatically. There's really no reason to have a separate source for connectivity information. When you know that an application on some host is allowed to talk to another host, and you have all the provider context in terms you know where these VMs are running on, you can automatically configure your network to allow for that connectivity. So it really doesn't matter how it gets there. It doesn't really matter how a packet gets from A to B. What matters is it should only get there if it's allowed to, and it should get there as fast as possible while fulfilling all the constraints that you have set in your policy. So how does OVS fit into this picture? Since this is the OVS conference, I want to make this about OVS specifically. That's why I kept the group-based policy intro as short as possible. In particular, OVS is a perfect example because it gives you the programmability that you require for an intent-based topology like this. On this side of the slide, we have our guy who's defining a policy. He would like to do that in a context where he has an orchestration system like OpenStack, and he would like to do that in a context where he has an SDN controller like OpenDaylight. I'm listing 2 open source projects here because that's my primary interest, but these could be other controllers, it could be other orchestration system too. These components are aware of group-based policy. So essentially, you can leverage existing APIs and new APIs that are built into these components to define your intent. At that point, the intent gets translated to OpenFlow and is used to configure Open vSwitch. So in particular, we're not modifying Open vSwitch in any way. We're leveraging existing APIs and merely translating user intent to OpenFlow. So this is an extension or a layer on top of OpenFlow which simplifies how you can define, how you define policy and connectivity. I specifically say overlay here. It's not, this is one of the strongest concepts, one of the strongest points of this concept. It doesn't really depend on, for example, VXLAN. Overlay could mean that, it could be a logical overlay, it could be IPv6, naturally. So you don't even have any kind of encapsulation. If your data center is capable of running native IPv6, you could use it to provide segmentation and do multi-tenancy without your user ever requiring to know about that. In another data center where where you don't have that capability, you might run VXLAN. In another data center, you might run Genève, or you fall back to VLAN. Doesn't really matter. Your user, your application developer does not need to care about that aspect. Another very important point is that the underlay needs to be vendor neutral. We don't want to depend on any vendor-specific features or technologies. So this is awesome. This is great, and it's in particular possible because OVS is written in software, so in software everything is possible. So we can provide all the features, and we can build huge abstraction layers. It's beautiful, right? In the software world, it's beautiful. It allows us to create beautiful diagrams. But what about throughput and latency? In the end, that's what it matters. Whatever solution we build, if it doesn't scale, if it doesn't perform, it is of little value. How do we get to ludicrous speed +1, right? We have heard from Rackspace at OpenStack Summit that OVS has done or has been able to make huge progress in terms of performance. I think that hardware offload is a concept that can drive it to yet another higher level because we can effectively reduce the overhead of packet switching to almost zero. One thing that comes to mind, and that this is a question that has been popping up over and over the last couple of years. Can we leverage SR-IOV? When I say SR-IOV, I don't specifically mean SR-IOV and how it is being referred to over the last couple of years. What I really mean is a concept like SR-IOV. What I really mean is, can we leverage virtual function, queue redirection? Can we offload the selection of the guest to the hardware? If eventually this results in something that does not depend on virtual functions, that's fine. The key point here is to leverage hardware capabilities in a vendor-neutral way while preserving the flexibility that the software provides us. And OVS seems like a very good candidate for an abstraction API because it already is at the point where it is already abstracting hardware, right? It abstracts hardware-specific details or kernel-specific details and provides a universal generic OpenFlow API. So it's a perfect candidate to be an abstraction API in terms of hardware offload as well. The problem is that SDN plus SR-IOV is really hard. Right? In software, anything is possible. Right? You can build anything you want. Particularly, that's why OVS rocks, because we can have an idea, we can start writing code, and all of a sudden it would start working. We don't have to go through years of development. Essentially, you can git clone, you can hack on it, and you can see your results. The problem is in hardware, you always have this constant feature gap in terms of software release cycles are shorter than hardware release cycles. So whatever you do and no matter how good the hardware vendor is keeping up, there is always a feature gap between what software can do and what hardware can do. And the last point is that resources are not unlimited on the hardware side, right? You have a limited number of VHAFs, you have a limited number of queues. Your flow setup rate is limited. You cannot assume that you can just offload everything to hardware and it will work fine out of the box. So what we need is some kind of fallback mechanism that allows us to fall back to the host CPU whenever the hardware is not capable of doing it, or whenever we made a mistake on detecting the capabilities of the hardware. This is how hardware offloading has worked in the Linux kernel for many years, and it has been very successful, right? Most of the hardware, or all of the hardware offloads in the Linux kernel are completely transparent. You can enable them, and they will work in the background without you ever noticing. There are some side effects, stuff like you might see checksum errors in your TCP dumps because the checksum has not been generated yet because it's done in hardware, but that is a known, well-documented side effect. Essentially, the offload itself is completely transparent. And I would like to go into the same kind of, use a very similar mechanism for OVS as well. And in order to do that, we need a fallback. And I would like to walk through how the fallback looks like. So on the left side, we have different types of encapsulation protocols. So this could be IPv6 here as well. It's not necessarily limited to encapsulation protocols. Packet goes into the eSwitch. When it sees the packet for the first time, it's obviously a flow miss. So it would go to the software table. Software table that would refer to the OVS kernel data path flow table. We would do a lookup. If the flow is here, we go to user space, obviously, just like OVS works. At that point, we know where the packet needs to go. Depending on whether the VM is running in software or whether it's attached to a VM, whether it's attached to a VF, we have two options. We can either go through the pure software path, virtual for VMs or VF for containers, or if it's running on top of a VF, we would actually send the packet back to the NIC, back to the network card, but we attach a tag which contains the VF where the packet needs to go. This allows for a VM to run on a VF, and we can reach it even if the packet goes through the host CPU. This does currently not exist inside the Linux kernel. You cannot send it back. You cannot attach a tag yet, but it's absolutely doable. Then when next packets come, the eSwitch would be prepared, and they could be sent to the VF and therefore to the VM without ever hitting the host CPU. Now, obviously, this fallback is not intended to be the primary driver of this. Essentially, and that's what John is going to talk about, we want to detect the capabilities of the hardware before we configure the hardware, meaning that we want to know what the hardware can do, what kind of actions it can execute, what fields it can match on, and configure the hardware properly. At the same time, there will be cases where we should send the packet to the host CPU. That's cases like keeping the connection tracker happy, right? We need to feed the connection tracker with packets so it can synchronize and keep its state. For example, we need to send it the TCP handshake packets. We need to send it the reset packet, TCP reset packets, so it can know when to shut down the connection. We need to continuously send small updates to the connection tracker so it will not expire. So this is not a trivial problem, but it's absolutely doable. Another example that Johan mentioned is if you're having a sniffer attached to your NIC, you want to take out any hardware flows and make sure that you send it to the host CPU so your TCP dump works as well. So how do we model this in the hardware, or how do we model this in the kernel? Typically in networking, we've always taken an approach of adding more layers. So why not just do that, right? So that's the current state on where we stand regarding this work. And this is not my work. I have been involved, but there's a lot of people involved in this. Some of them are in this room, others are not here. This is essentially a collaboration work by the kernel community and the OVS community. Where we want to get to is we want to have a new SwitchDef offload API. SwitchDef represents switching capability in hardware. This is not limited to OVS hardware. this is actually a mutual goal from both the server-driven use cases and the switch management use cases where people actually want to use a Linux API to manage hardware switches. So this is the base layer, and this provides us an API to program hardware in a vendor-neutral way. The vendor-specific parts would be in an offload driver that sits inside the NIC driver. This NIC driver will have implementations which are specific to the capabilities of the hardware. If the hardware can talk P4, then the driver should use a P4 interface. If it's a traditional L2, L3 device, then it should talk whatever the hardware understands. If it's a flow table-based device, it might even talk OpenFlow. On top of the SwitchDef API, we have an Offload Netlink API, which allows to export the capabilities of the driver and / hardware to user space, and at the same time configure flows back into the hardware. An OVS would be a user of this Offload Netlink API, where we have a small new component inside OVS. Maybe it's not that small, maybe it will grow bigger because it's apparently not that simple to get this right. But it will drive the offload decision, deciding how to map a software flow configured in OVS and put it into hardware. The beauty of this, and this is in particular very important whenever we work with the Linux kernel community, whatever we add needs to work for all the components involved in the kernel. So essentially, this offload API will be consumed by the QDISC/TC components as well. This is actually great for OVS because OVS leverages these components to do QoS. So while taking this additional step of making sure that it can be consumed by everybody, we can actually benefit as an OVS community and have hardware offloaded classification, scheduling, etc. Other uses would be the Linux bridge, even NF tables, IP tables could make use of this. One thing that I didn't mention so far is that this model is compatible with the DPDK approach. Essentially, due to the bifurcated driver model, you could run a DPDK application on top of a queue, and you could insert flows into the hardware, which would redirect packets to a specific queue. And on that queue, DPDK, a Polymer driver would be running, so you could integrate your DPDK applications into this model as well. With that said, I would like to open up for questions.
Does anyone have a question?
Amal Broadcom. So what's the current state of the offload API that you were proposing, the Netlink and SwitchDef?
So the SwitchDef API has been posted to the NetDev mailing list a couple of times. It went through, I think, 7 or 8 iterations at this point. It's very close to merging. I will let John comment on the actual state of the hardware capabilities interface and on the flow addition and deletion API. But we essentially found consensus in one of the last developer conferences, and we're working towards a mutual goal, and it seems we are making a lot of progress.
Thanks.
I would like to point out that if you have any questions or if you're interested in Groupees Policy, we have a couple of guys from our team here, and they're glad to talk to you.
Frank from Cosmos. So, do you have also tunnel endpoints decapsulation like VXLAN in this API or not?
Yeah, VXLAN is definitely part of this API. So this would be the capability to do encap for VXLAN or decap for VXLAN would be exported through the hardware capabilities API, and it would be an action that you configure. So if you have an OpenFlow action to add a VXLAN header, if the hardware is capable of taking that action, you can offload it.
How extendable is the APIs? Is this like a functional API, or is this more something that you can define more APIs, more functions that you find to offload?
I think it is very extendable, because the first thing we figured out while trying to collect common use cases and trying to find consensus is that everybody wants to use this for a different purpose, and hardware is very, very different. And I think this relates back to Johan's talk. We figured out that there is an open flow world, there is a traditional L2, L3 world, which has completely a different approach on how the APIs should look like. There is an approaching, there's an emerging P4 world, which is yet different. And it seems difficult to consolidate on one single API. That's what's being represented by the boxes down here, right? The SwitchDev API here will provide different API or different levels of abstraction APIs in terms of, some of them might just be an open flow path through. Another one might be the OVS flow key, just push that through. Another one might be something very similar to how Linux handles L3 right now.
I'm talking about, yeah, I mean, if it's a forwarding table, it maps with OpenFlow, but there are certain operations that OpenFlow doesn't support. What is the extensibility model, so we don't stifle innovation?
So it's not OpenFlow specific at all, first of all. So if there is additional need for something that is not covered by OpenFlow, that can be added, no problem, right? It's based on Netlink, and Netlink is in particular built to be extendable without breaking backwards compatibility in any way. So if there is an additional feature, action, match that you need, and you find consensus in the community that is useful, there you go, you can add it.
Just to be clear, that was the NetDev community. You weren't talking about the OVS community, in terms of adding the features to like SwitchDev.
Yeah, I think you will need, thank you, you will need consensus from both, right? You will need consensus from the OVS community, and you will need consensus from the NetDev kernel community, which will have a saying in this as well.
We have time for one more question.
So do you also see it as doing routing offload, not just sort of switching? So you just push the rib down there?
Absolutely. I think, well, first of all, you can do L3 with OpenFlow in some way, right? But you can also leverage, for example, or it's definitely intent to offload the existing Linux kernel L3 forwarding path as well. So I think both.
If you had a traditional layer 2-3 switch chip, it has very large.
Exactly.
Layer 3 tables.
Yes, exactly. So in that specific case, the mapping from the traditional L3 forwarding in Linux maps very well with these traditional L3 switches.
All right, let's thank our speaker.